Okay, so the issue is that why is it?
Use slideshow.
Okay.
Why did you? Yeah, can you use that slide?
This one?
Yeah, yeah.
Is it good, D, over on your side?
Yes, all good on my
Okay.
side.
I just had to switch to slideshow properly so that it is good here as well. Okay,
Great, let's get started.
let's get started.
Right.
Yeah.
So it's my pleasure to introduce Dr. Omar Khan. So Professor Khan is a professor at the UNBC at the University of Connecticut. He leads the computer architecture group and also serves as an associate director of the Connecticut Advanced Computing Center. His research interests include computer architectures that support parallelism, locality for high performance applications, such as graph intelligence problems. He has contributed architectural advancement for futuristic massive parallel microprocessors that substantially enhance system level performance, security, and efficiency. Prior to joining UConn, Khan was a postdoctoral research scientist at MIT. He received doctoral degree from the University of Massachusetts Amherst. He spent several years in the semiconductor industry as a high-performance processor architect. Without further ado, let's welcome Professor Khan.
Thank you so much, Fan. It's great to see you and great to see everyone here. So I'll just get into it. Okay, my name is Omar and I'm from UConn. I'm going to talk about graph intelligence problems today. So I'm going to walk you through a set of the way I look at this problem is in three eras. We had the first era where we had looked at traditional graph processing, and there what we have tried to do as a community is to extract meaningful information from this non-convex decision space and make some sense out of it. For this, there's been a lot of deterministic algorithms that you operate on graphs with. These are computational and memory bounds. But the main challenge here was this strong input dependence. Graph input dependence has hog performance scaling on in a parallel setting. In the second era, which we have been kind of in the last 10 years, been spending a lot of time on, is this integration of graphs with neural networks and graph transformer networks. And the idea here has been automate these graph analytics, learn patterns in relationships, and makes decisions out of that. The main challenge here has been this massive growth of data, because not only is there graph, there is a neural network integrating within the graph. That further stresses parallels. And the third era, which I see coming up in the future, is this multi-objective graph processing era, which I will talk a bit about what we are trying to do there. Here, the idea is that we want to co-optimize multiple objectives to make decisions and not have to kind of rely on inaccurate decisions, but come up with exact accurate decisions for high for applications that require that kind of space. The challenge here is these are non-deterministic hard problems, and as I'll discuss throughout this talk, which leads to very complex underlying operators and data structures that need to scale on modern parallel hardware. Okay, so let me dig into it. I'm going to walk you through these three eras. I'm going to go rather quick through the first era because I think everyone here has an idea about how graph processing works. So graphs have been pervasive in our AI infrastructure. Everywhere you go, look at asset forecasting, recommendation systems, social networks, everywhere there are graphs. There are many challenges in graph processing, and I'm going to try to identify them and then see if I can build on them over the talk. The first big one is they're getting bigger in size. There's a lot of sparsity in these graphs. There's a lot of irregular, unstructured connections in these graphs that lead to a lot of frequent data accesses, but to unstructured places in the data. And the last part that is really important in graph algorithms is that they like to operate on tasks that are ordered. If you don't order those tasks with some notion of the algorithm, there's a huge hit on work efficiency. So the parallelism is on one hand important work efficiency for these algorithms carries a lot of. So exploiting this parallelism is a hard problem. We looked at about 10, 12 years ago, we built a graph processing, get rid of this guy, which started characterizing these graph problems that were emerging. Parallel hardware was taking shape. We were starting to see more than 10 cores, 20, 30, 50, 100 cores type of settings. So we evaluated, we built a simulation environment where we evaluated a bunch of traditional graph problems. And what we found was that the data access and the communication is the key limiter in scaling graph problems. So then we went on a bit of a ride to see how we can innovate on the architecture front, which involve hardware and software. So I'm going to sample a few things, talk a bit about the challenges and what we have done. Hardware challenges, what we found here is it's all in the memory. You can see everything is memory. So memory systems, they walk through where computation is all the way to where the memory actually resides. There latency gaps, 2 orders of magnitude latency gaps, and in you accessing the compute unit versus you accessing data from the main memory. And there's 1000x energy gap, which leads to another order of magnitude challenge to keep the efficiency high on these systems. Memory has increasing complex trade-offs. We have built deeper hierarchies of caches. There's been heterogeneous technologies, CMOS with X technologies being built that add more challenges to the latency and energy woes. And then in the architecture side, not just we have integrated caches, we have integrated scratch pads, buffers, registers, massive amounts of them so that we can move the data more and more efficiently. And then the consistency of memory, the coherence of data has been a hard problem to scale in this thousands of core setting that we needed to scale these problems. So I'm going to sample a few things that we worked on. These took multiple years to build, so I'm going to try to tell you about them in one slide at a time. This was one chip we built. We spent a lot of time during my time at MIT, where the idea was, can we chunk data in 6 locations and move computation to the data? So you shard data, you keep chain memory paradigm, and then you are constantly migrating data so that you can get locality through cache aggregation. This also allowed us to reduce network traffic because you're not moving data to the computation, moving computation to the data. So we built some chip here back in those days, 45 nanometer IBM technology. We were able to, our main idea here was how do you migrate threads without doing a lot of handshaking. So we built a one-way deadlock-free migration protocol where a thread decides it's going to operate on chunk D. It will autonomously migrate to that chunk D, perform some computation and die there. So it was able to show some ideas there. And I'm going to kind of summarize these hardware ideas into a notion that I want to carry forward. Then there's another set of work that we did was this idea of locality-aware cache coherence protocols. Everybody here has seen cache coherence protocols, distributed cache coherence protocols. What we did was we built the idea of locality classification in hardware, where you are looking at the data, looking at how much it's being reused, and classifying it on the fly in the hardware, and then having hardware classifiers decide whether you want to cache that data, whether you want to bypass caching that data and go straight to the next level of the cache hierarchy and so on. And this way you're eliminating a lot of unnecessary burden on the data movement costs. That led us to improve the access latency and energy consumption on these complex cache hierarchies. And then there is another piece of work that we kind of evolved into was to see if we can enable asynchronous messages on the system so that these messages can take the compute to where the data is, and then operate. And we use this to actually build explicit communication, which kind of operated as an auxiliary method to your traditional cache coherence paradigm for asynchronous data access enablement. So now we can actually support non-blocking loads, non-blocking stores, what traditionally there, but non-blocking loads more specifically to unlock scaling to larger core counts. Okay. So that's the sample of the hardware space. I just want to quickly run through some of these ideas. The essence was build asynchronous data access protocols. Now, the software is also as important, maybe more important than the hardware, because you have to devise the right software primitives to manage these complex hierarchies, these complex protocols. These hardware protocols are not worth anything if the software is not taking advantage of these primitives. So one of the key findings that I have in terms of the graph processing is, if you look at graphs, there's a lot of input dependence. The algorithms, they bring about irregularity, sparsity, ordering requirements. So this software that is actually now operating on these highly input dependent paradigms has to very quickly adapt to your optimal settings. And the optimal settings are within the hardware, and even the accelerators started exploding in terms of GPUs and CPUs. And we wanted to see what type of software ideas we can explore. So one thing we built was this idea of a graph performance predictor, where you can look at your inputs, you can look at your algorithms, you can look at your machine's capabilities, and can you co-optimize them to find the right software configuration or find the right parameters in your software so that that particular instance that you're trying to solve can operate optimally. So the key learning here from this work, what we found was that these graph problems don't just uniquely stress GPUs, they also stress CPUs. They are not only throughput bound, they are also very much latency bound. If you don't do latency optimized implementations of their software, you're not going to get good performance. You can have very high throughput, but you're doing a lot of garbage work if you're not efficient in managing your operations. So we started doing things like task speculation. So inside graph processing, what we identified was that every time you're doing any computation, it's called a task. You pick a edge or you pick a node, and then you're performing some computation for it in terms of its relationship with other edges and nodes in its surrounding. That's in essence what you're doing to do in every graph problem that you try to solve. So these tasks, I mean, in this example, I'm going to show you a little graph with A, B, C, D, E, nodes connected through some edges, and you're doing Dijkstra. Everybody here knows Dijkstra, trying to find the shortest path. Now, if you order these paths that are enabled by this little graph, you can see on the right-hand side that some tasks are created, but some tasks have lower distance from the source node. So those are high priority tasks. If you create the same task B with a larger distance, it's a bogus task. It's called a speculative task. It's an unnecessary task. I don't need to compute that task. So if we can actually speculate on tasks, we can unlock a lot of parallelism. But then if you keep processing in that speculative way, we're going to end up doing a lot of processing on these orange tasks, which is unnecessary. So can we actually speculate at runtime, but also detect redundant paths through software checks and see if there is a path that is now transforming, starting from the middle B, the orange version, and it's starting to explore the graph in the speculative dimension unnecessarily and kill it. So we built a software paradigm where we can detect those paths from progressing and kill them before they unroll into unnecessary computations. So that unlocked parallelism with high work efficiency. And then just to kind of stress more on that ordering paradigm, we also built this idea of a priority drift aware task scheduling. Here, the idea is that you want to maintain that priority of those tasks. So what we do in graphs is we maintain priority queues which order these tasks. And these tasks are then put into a priority queue. Now, if you have a single priority queue, it's not going to scale in a 1,000 core or multi-thousand core setting. So people do distributed priority queues. So each core or each set of cores is maintaining a priority queue of tasks. Now, maintaining a high level priority among those priority queues is very hard. So we came up with this idea of a priority drift signal that aggregates and computes every so often the drift that each core is having with respect to other cores' priority queues. And if the drift increases, then we will take an action where, for example, if the drift increased, that implied to you that you have very high priority tasks running in the system. So let's start distributing them more aggressively. But if your drift decreases, then we found that, okay, there's no point distributing these tasks. You're already operating with less drift. Lower the distribution factor, don't distribute these tasks, save on communication costs, right? And so finding that balance between when to scale back on communication, when to let your cores distribute these tasks so that you can unlock more parallelism led to the development of this HTCPS scheduler that allows you to exploit parallelism without drifting in priorities. Okay, so I want to just wrap this era one and go more towards the newer era. This is an kind of like a refresher, hopefully, to everyone. What we have found is this lot of strong input dependence, a lot of unstructured, large amount of data that we got to work on, right? Hardware side of things, if we want to go to this many thousands of core paradigm, we have to unlock data movement in these complex memory hierarchies that we are building to enable these systems. And on the software side, we have to make sure that these tasks can scale. So we have to build technologies that can be order aware. If we drift too much from the order of these tasks, you lose performance. And if you don't, then you can take advantage of it in terms of parallelism. So that tension you have to balance. Okay. So at some point, we transitioned to this era where graph processing started making progress towards automation, right? So the idea of deep learning techniques evolved in the last 10 years, and folks that work on graph processing, they thought that it's a good idea to automate this domain of graph processing. So people started integrating graphs from different aspects like road networks, from chemistry, physics, social network engineering, all these areas. They started building neural network models and integrating them in those graphs so they can solve these problems without really having to theoretically come up with a bounded algorithm. This led to massive graphs, and these led to larger and larger and larger GNN models, graph neural network models. Now, these GNNs, they compute on these nodes and edges, but each node and edge is now a vector, right? So not just a scalar quantity, it's now a vector of learned information. So these vectors are what your neural networks are trained. And that leads to these graph proportional matrix operators that you have to perform, because now you're not just doing graph processing on scalar elements, you're doing graph processing where the graph can be imagined as a matrix with another embedding matrix, right? Good news was it automates graph processing. That's good, very, very useful. There is a blow up on the computational and memory costs, and then we are paying on decision accuracy. I'm going to get to the decision accuracy as I roll down the era two a little bit. There is this notion that we can do automation, but it comes at a big price. we pay 80%, 90% accuracy. What about that 10% that you're inaccurate? In a high stake environment, that can be very costly. But anyways, in these graph proportional operators, what we did was we did a bunch of analysis on the GNN model. We took 10 or 12 state-of-the models a couple of years ago, and we started analyzing them. If you look at it, this left top picture is showing you the graph can be represented as an adjacency matrix, right? And then the embeddings are now vectors where each graph vertex has its own vector array, or every edge can be represented as vector. So we'll call this an embedding matrix, right? And then you have a model that you have trained with weights that you can apply on these two inputs, and through some convolution, you are computing the output, and then this process is repeated multiple layers to learn something about the graph, right? That's the paradigm. That's an abstract GNN model. We kind of broke it apart, and through different operators in how these models operate on, we found that they all boil down to either the dense matrix multiplications, or sparse dense matrix multiplication. Sparse dense because this guy is pretty much always sparse. The graph is always generally sparse the way we know it today in today's world, right? So you're really operating on those. So one of the largest models, I'm showing you this Amazon products model with probably the largest number of non-zero elements in that graph. I think it approaches hundreds of millions of edges that we could run on a single machine. You can go to larger models. Even Alibaba has 100 billion edge model. So it's kind of crazy. But we characterized these models, and we found that these sparse matrix operators are taking about 90% of the time. Even though you have a lot of gem operations, they run really fast. They're much more efficient. But these sparse operators don't scale on modern hardware. And they take 90%, almost 90% of the time. So what is the challenge with these, right? So these SPMM operators, they are graph dependent. Their size is graph dependent. So your number of rows in those matrices are graph size dependent. You have millions of rows, then they grow. They have a lot of variability. They're large size, they're ultra sparse, and the irregularity of the graph translates to structures like this, where you are following these power law behaviors across the node edge connections, right? Where you have some nodes with very few edges connected and some nodes with these evil row number of edges connected. We call them evil rows because if you happen to run this and distribute this by using the x-axis of these graphs among a parallel substrate, you're going to find that the longest guy is going to be your performance limiter, and you're not going to be able to exploit parallelism. So how do we exploit parallelism in these kind of highly unstructured graphs? These are 4 different domains, and you can see that the shapes are totally different shapes. You can't predict them statically. You have to learn them as the data comes along. So we built some ideas. So we had many people at that time build hardware accelerators for these graph neural network models, and specifically the SPMM acceleration was something that they focused on. So we added to that literature. I wanted to give credit to folks who have built hardware and GPU accelerator frameworks in this paradigm. We're not the only ones here. And even in the past works that I talked about, there's a lot of other players. So the SPMM accelerator that we have looked at, it introduced this concept of the merge path to load balance, distribute the work. So these evil rows don't get to hog the parallelism. What we do here is we co-optimize locality and parallelism. So effectively, there's a trade-off and a tension between how much parallelism you can enable by distributing the work in these adjacency matrices representing the graphs, and how much work do you end up doing in a given core. If you do too little work, yes, you can unlock a lot of parallelism. If you do too much work, then you're serializing. So finding that right balance is very much graph dependent. Depends on the number of nodes, number of non-zeros in that graph, which is the basic characteristics of that graph. So finding that balance, we propose an online scheduler that can learn and adapt. Another thing that we found, which is the bottleneck in the SPMM, is this red path, where if you have the rows of the graph, and then you are looking for the edges that that node is connected to, that edge connection is highly irregular. So when you find that edge connection, you have to go now fetch the embedding vector associated with that edge, right? And so that is an indirect access when it comes to the underlying software that is executing that that computation. This indirect access leads to a load that cannot be predicted a priori. So scheduling the load becomes a really hard problem. So when you get to that edge and you need that vector data and you issue the load, it's generally too late. You're now going to wait for that load to be processed in the underlying hardware, and that hogs parallelism. So we proposed indirect data prefetcher that can, it's a software hardware kind of collaborative prefetcher that tries to do a timely load for this embedding vector in a 1,000 core type of setting. In a few hundred core setting, it's a little easier to imagine how to time these loads, but in a 1,000 core settings, you're talking about 1,000+ cycles before you can get this data. So you have to really time these loads ahead of time to really take advantage of prefetching as an idea. So we looked at some of that ideas and developed some decoupled asynchronous paradigms through these ideas to accelerate the SPMM operator. More recently, in the last 2-3 years, we said, okay, we can accelerate these operators. That's one paradigm. What other things we can do? So one idea that we came up with was, and this was something that was already happening, a lot of people were taking the graphs and injecting sparsity in them. Meaning, take a graph, you may have node connections that you don't want, they are unwanted, they are maybe redundant. So they can drop them. They can drop edge connections without really sacrificing accuracy. What we brought in there in that space was, we said, what about the model? Can we actually inject sparsity in the model and sparsify these embeddings so that we can reduce the load that we have to process? This brings about a massive opportunity, because what we can do now is, not only the graph is getting highly sparse, the embeddings are getting sparse, we're reducing the total number of flops you're going to do, and we're also reducing the number of bytes that I'm going to have to process. So if I can take advantage of that, then I can unlock performance. So the question that came about with this was, first of all, how do you unlock this sparsity? And number two, how do you exploit this sparsity for performance? Two separate issues still outstanding, both of them. We've done some work on it. Hopefully, we'll keep working on it more. So the sparse training was one thing that we built. There are two frameworks that we built and published them. One is a sparsity, a structured sparse training, and other is unstructured. Two different works. I'm going to try to put them in the same slide so you can contextualize it for you. Okay, they both have your graph adjacency matrix common, but on the embedding matrix, what the structured sparsity does, which our prone GNN framework was published last year in HPCA, the idea here is that we can inject structured sparsity into the model. So you're basically dropping rows or columns at a time, meaning you're dropping either a whole edge across the whole graph, or you're dropping nodes in the node vectors in the graph. and unlock sparsity. So if you draw columns, which is what we built in the Brune GNN framework, what you end up getting now is these low dimensional SPMs. Okay, we'll talk about that in a second. On the right-hand side is an unstructured sparsity paradigm. Here last year's S+, we proposed a new operator called max K operator. So you replace your ReLU operator with a max K operator, which sparsifies the embedding matrix in the model. Okay, but it sparsifies it in an unstructured way. It doesn't have any notion of columns or rows. It will sparsify anything that it can find. The good news there is it's going to find a lot of places to sparsify. And that leads to this kind of a unstructured sparse matrix. What happens with these operators now is now our sparse dense multiplication has become more sparse multiplication, which is even harder as an operator to scale. So we then so we unlock these frameworks, but then the question was, can we take advantage of performance in these resulting operators, right? So if you look at our low dimensional SPMM, if you think of a GPU or a highly vectorized machine, you're effectively taking a chunk of work in a given thread. They call that your warp or a SIMD unit in a GPU context. And you map that work and it operates on the vectorized lanes by mapping the dimensions of your embedding matrix on those lanes. Now, if you go highly sparsified model, those lanes are not fully occupied. You will end up occupying 10 lanes, 8 lanes, 4 lanes, 2 lanes. In some of the models, we go down to a dimension size of 2, 4, right? So what happens in this paradigm is your hardware is getting underutilized. You're not taking advantage of the hardware that is under the hood available for you. But the idea of block reduction and byte reduction was there. The potential of 100x, 75x reduction in bytes was there to unlock that performance. So what we proposed to deal with this hardware challenge was a decoupled asynchronous execution model where you unlock some of the hardware capabilities in these modern machines where we can do sub-warp level mapping. So we call that virtual flops. So you map the work inside the warps or inside the vector units by distributing the work and running them as independent threads. Okay. And the idea is to kind of decouple that accumulation update of that SPMM to a point where the communication can be minimized so that you can unlock more and more of the throughput of these operators on these highly vectorized machines. So with this Prune SPMM operator that we built, which follows this decoupled paradigm, we were able to unlock up to 3 terabytes per second memory bandwidth on a H100 machine, which gives you about 4 terabytes per second. So that kind of is literally state of the art at this point in terms of how much bandwidth we were able to unlock for these operators. And that improved throughput by over 2x over SOTA in that context. In terms of the sparse dense acceleration, we applied the same idea. Here, there was more sparsity. There was more reduction in flops, less reduction in bytes because these sparse operators, when they operate on these two sparse matrices, they accumulate into a dense matrix. So this is not your traditional SPGEM operator. This is a new operator that produces a dense output. So what you're doing is you're accumulating at very low width, but then your output is always at a full band. So this creates this heterogeneous operator data flow. And so managing that data flow on the hardware is not that trivial because it requires communication between accumulation and updates. So we put together this decoupled execution model where the accumulation also takes care of the lanes that are available, and when you go to the update phase, you serially coalesce way update the outputs in an efficient way by taking advantage of the throughput that is needed in this paradigm. Okay, so I'm going to kind of try to wrap up this second era so that I can spend some time on the third era, which is going to be kind of new to you guys. So the idea here was we could automate graph processing with AI integrated, right? Unlock sparsity, unlock acceleration of these operators that I talked about. And we have built some hardware ideas, some software ideas to deal with those things. We are looking at this idea of a sparse vector core. Like you have this tensor core, can we redesign from ground up a sparse core that can operate on these kind of sparse vectors? I'm not going to spend any time on that. That's ongoing work. I can talk to you about it offline. But the problem here with this era is that this automated graph processing has this explainability problem. I can process this data. I can tell you I have 80% accuracy. What does that mean to the end user? There are many end users who don't want approximate solutions. They are deploying this in a mission environment. Solution accuracy is really key. So for this, I'm going to move you into this third era, this multi-objective graph processing. Because effectively what you're trying to achieve with these graph neural networks and such is being able to do graph processing in a multi-objective setting, where you're trying to optimize multiple objectives to come up with your decisions, right? So now you have a graph, you have multiple objectives, like time, fuel, your weather conditions. There are many more I can talk about. You would argue, well, why can't I pre-process all of that data into a single objective and solve it as a single objective? These objectives are non-convex. They can't be pre-processed into a single objective. I'll give you an example. This is a real-world example from US Navy, where you have a vessel, you want to route a vessel to some place. If you do use your traditional shortest path, you can compute this green path. But in future time, there may be a hurricane that evolves, and you may get interdicted by that hurricane, and that can be destructive. So in this scenario, you need to not only make the decision based on the shortest distance or shortest fuel, you need to make the decision based on a combination of those things with the weather that you are going to encounter. That is evolving, that changes. Every hour it changes. And how do you route these multi-objective optimization problems with exact solutions is absolutely crucial to be able to deploy these things in practice. Yes, yeah.
So I guess I'm still not clear what you mean by multiple objectives. It appears to me like the objective is the same, which is to reach from point A to point B, but you have more constraints.
Yes, we have more constraints, but these are called multi-objective problems because an objective is, I want to be able to compute on this graph based on fuel cost. I want to optimize fuel, right? Or I want to optimize distance. So your traditional problems, they are single objective problems, right? You're always minimize distance or min. So that's what I mean. You have multiple objectives. So in the classic graph theory, they are termed as objectives.
Not constraints.
Not constraints, yeah.
Optimize this subject to the following constraint.
Yeah, you can think of it that way too. From the constraint programming standpoint, that is the way to think about it. Yeah. But good. Hopefully that notion will stick with you for now. Okay, so maybe this clarifies it. If you look at your single objective world, you normally have a graph, node, edges, right? And you have a single cost. That is your objective that you're trying to minimize or you're trying to maximize or whatever, right? And then you compute on that. We all know many algorithms that can give us a deterministic algorithm. And so, for example, you could find this cost, the optimal cost where that vertex settles, and then you can trace back and you get. In a multi-objective scenario, you have the same kind of graph, but at any given node in that graph, you have multiple objectives that you're trying to optimize. So what you do is you generate these so-called labels, and I'll build on these labels. These labels are these cost vectors of objectives where multiple objectives compete in different ways, and you can now have multiple labels that exist for a node, and multiple labels can be Pareto optimal for that node. So you're not trying to optimize for one cost and settle on a cost. You're now aiming to settle on a Pareto optimal front for that node. So in a multi-objective algorithm, what you do is you want to compute the Pareto frontier for all the nodes in the graph. Once that Pareto frontier is computed, like this, these dark red labels are computed, you have all the Pareto frontiers, and now you can take your decision component and say, in this case, I want to trace back on a shortest path that co-optimizes some D objectives. I can pick this labels path or some other labels path, so I can have multiple co-optimized objectives giving me multiple exact solution paths that I can now traverse, and they all are co-optimized for those objectives. In this case, weather was one of the objectives. It was able to avoid this hurricane while being able to give me lower fuel costs and maximize my distance objective as well, right? So that's the, in essence, is this problem. This problem is NP hard. Computing these frontiers is an NP hard problem. We want to solve these problems because our users want these problems. Okay. Did I do something? Oh, any button here?
Yeah.
Okay, thank you.
Okay.
Okay. So say the vessel example, I'll talk a bit about this this graph in a bit later in a second. But let's say you have a graph like this, you're trying to route this vessel, and you have a graph with edges and connections. We characterize this on with a sequential code. What you find here is that these labels increase by 3 orders of magnitude when you go from few objectives, like 2 objectives in this case, to 12 objectives. Okay? Your runtime skyrockets from milliseconds at 2 objectives, not just one objective. One objective can be in microseconds, to an hour in 12 objectives. That's the explosion in work and complexity that we are talking about in these problems. Okay, so what are these underlying algorithms and why are they so massively computationally explosive? So in order to understand that, I'll have to give you an overview of what it looks like. These problems have labels. So these labels, we're going to put them in 2 sets, an open set and a closed set. A closed set will contain all Pareto optimal labels at that given time. And we're going to keep computing these labels and keep putting them in the closed set as we find Pareto optimal labels. And eventually, when we will settle on this algorithm, we'll have in the closed set all the Pareto optimal labels that we want to compute. Open contains all the unvisited labels to explore. Okay. Now we maintain open with 2 data structures. They'll become a little bit clear. One is a queue, the other is a set, and this is done for efficient processing purposes. But they are mirror of each. First thing, order is very important in this algorithm. Open is a set of labels that has to be lexicographically ordered. We can't just create one order because we don't have one cost. We have multiple costs, multiple objectives. So the best we can do is create a lexicographical ordering of those objectives. You take the first objective and then you the next objective and the next, and that's how you create a lexicographical priority. Okay. This ensures that we are extracting a Pareto optimal label for processing at any given time when we are processing this out. Okay. And that enables optimal number of labels that we're going to process to come to the conclusion where we're going to find our Pareto frontiers. Clear? Okay. Next, you extract that label from the open. And now that label is supposedly a Pareto optimal label. If it's a regular nodes label, we just put it in the closed. Just remove it from open, put it in closed. if it's a goal node label, that's the goal node that we're trying to reach in this algorithm. We're trying to, in this particular case, we're trying to find a shortest path, a multi-objective shortest path. If it's a goal node label, it's just supposedly a Pareto optimal label. So what we do is we see if in our solution set, which is part of our closed set, this is the solution set for the goal nodes labels. These are other Pareto optimal labels that we have found so far. Do any of these labels dominate the fundamental operator that we're going to talk about? This dominance check implies that it is dominated by any label in the solution set, then this label does not belong in the solution. Dominance, if the path cost of that label in the solution set is less than the path cost of the label that I'm trying to insert into the solution set for all objectives, then that label is dominated by an existing label in the solution set, and I should not be inserting into the closed set this particular candidate.
Can I ask a question?
Yes.
Not sure, but I understand the dominance check is important, but can you give us like practical example? And I'm not sure how the weather can be dominated by something else.
Well, the weather is going to dominate your fuel consumption, right? I am gunning and I'm consuming fuel, and there is a hurricane, and the hurricane is synthesized into telling me that go faster or go slower, so that by the time you reach that point where the hurricane is supposedly going to interdict you, you either are slowed down or you're moving faster so that you can get ahead of that hurricane, and when the hurricane comes, you can bypass it. That is what we are trying to do here. We're trying to co-optimize these multiple objectives so that we can come up with a path that not just tells me a speed to go at with which I'm going to consume the minimum fuel. It allows me to consume the fuel, minimize my fuel cost, but at the same time, not get interdicted by that hurricane. And so that translates to these multiple objectives. The data is synthesized into these multiple objectives, and these objectives are co-optimizing for that shortest path. That's in essence. We can talk more examples down the road, right? The complexity of this dominance check grows with the number of non-dominated labels in that solution set. If I have a lot of solutions in that solution set, I have to compare each label to that label to come up with an answer whether this label is dominated or not. There's some good news. If there is a dominated condition is met, the moment you meet the dominance condition, you can exit because you already found one label. As soon as you find one label that dominates it, you don't have to keep checking. So you can exit early. Now, these algorithms don't just do dominance checks. They realize that you are expanding these labels at a rapid rate. So they heavily prune labels that can be pruned. If you found a candidate label, now we have found that this label that we extracted is a candidate label. We can insert it in closed set. Can we prune other labels in the solution set as a result of me introducing this new Pareto optimal label into the closed set? So that pruning check basically removes these labels. This pruning operator under the hood is performing dominance checks, but it has to perform these dominance checks in the reverse order against all of the labels in that set. There's no early exit in this particular scenario, because if you want to really prune that set, you have to check everything, right? Moreover, you have an open set. You also have an open set of labels at this given time with all of the labels that are sitting in the open that you're going to be exploring in the future. If I have found a solution Pareto optimal label, supposedly, can it dominate other labels that are sitting in open? So this algorithm goes further and prunes the open. So there is that prune open operator is even more complex because it takes and prunes the entire open. Open can be millions, billions of labels at any given time. So you have to perform those pruning checks against all of those labels. Now, once you're done with this extraction computation, now that label is inserted in closed set. Now it's time for that label to expand. Meaning you found a Pareto optimal label for a node. That node is connected to other nodes, the edges of that node. Each edge is visited, each neighbor is visited, and the expanded label is inserted into the open. The expanded label is not allowed into the open unless we prove that this label is not dominated by any open or closed set label. Because if it is dominated by somebody in the open or closed set, what's the point of injecting it into the open? So we want to suppress it. So you have to perform these dominance checks against all open and closed sets. Now, open and closed sets are maintained on a node granularity. So these checks are only performed at that node level. So it's checked against all of the nodes for that, all of the labels for that node in the closed and open set. That's why we maintain an open set, not an open queue, because otherwise we would have had to search the whole open, right? And then once you find that it's not dominated, then there's a possibility that we can prune labels in the open and closed set. Because there could be other labels that we have in the open and closed set that we can prune out. So it performs a pruning operation as well. Now, given all of that, when we characterize this algorithm, now back to my characterization again, what we found was that as I increase these number of competing objectives, these pruning and dominance checks skyrocket in terms of number of labels that we are performing these checks on, and hence our number of labels increase rapidly. What we found was that we're spending most, if not all of the time, in doing these underlying dominance checks. So these dominance checks, they increase rapidly because you have increasing number of labels, and these number of labels increase with the number of objectives. If you have one objective, you have one label. With two objectives, you can have many labels. If you have 12 objectives, you are going to have many, right? And then number two, it also increases with the number of nodes in the graph. If the graph size becomes bigger, these labels become bigger. The graph edges become bigger, these number of labels explode. They keep exploding. Very high compute and memory requirements. But there is massive label level parallelism. Back to my roots, how can I accelerate this? Can I accelerate this problem and substantially reduce this burden of computation time? Well, there is a hurdle in there. The biggest hurdle is in this graph. These are your candidate labels. We took all of the candidate labels that we processed, and on the y-axis, I am plotting the number of actual dominance check that candidate label had to go through. And if you look at this graph, it's highly variable. It can be a few to many orders of magnitude, many labels that is checking, the check that is performing. So it's highly variable. Number two, I have to keep that order, that lexicographical ordering. Otherwise, I am going to put and extract unnecessary labels, and I'm going to expand unnecessary labels. So I want to keep this processing as close to the lexicographical ordering as possible. Right. So let me just zoom through this 5 more minutes, and then we'll try to wrap up. So we proposed MP-MOS. This is the first ever multi-objective parallel short spans algorithm, and it's a parallel implementation. What we do is this, in essence, we extract this num extract is a system parameter that you have to tune number of labels from the open. These labels then are performed in parallel for these dominance and pruning checks. We maintain a lexicographical ordering of these labels, and the algorithm terminates when the open is empty. So you have to keep iterating and keep performing these steps over and over again until the algorithm. There are 4 main parallel components. You have parallel extraction, parallel expansion, where you're doing the dominance operators. Compaction is something that we do for dynamic data structures. I'll talk about it. And sorting is for the lexicographical order. Because these are highly variable, we have to build a work stealing scheduler, where the idea is that we have open, we have num extract. So every thread in the system goes and extracts a label and start processing. Now, when we extract multiple labels from open at any given time, these labels can dominate each other. So we have to introduce a new dominance check in our parallel algorithm, where if a label is extracted, it first checks if all of the extracted labels, is there any label in there that is going to dominate this thing? And if it does so, it squashes it. If it doesn't, it keeps processing. Now, a label is highly variable, right? We saw that. So a label can come read, it's going to fetch a new label and keep processing. So that's our label extraction parallelism. Pretty straightforward, right? The dominance check is our core in the expansion phase, where we're doing all these dominance operations. I'll give you an example of how our vectorized dominance operator works. Imagine you have an LX label that you're trying to perform a dominance check against 8 labels, just for example, right? There are 6 objectives. So the labels are on the horizontal axis, these different colored labels. You perform the label comparison for the first objective. Let's say you find that 6 out of 8 labels are not dominated for these 8 labels. So in this example, I'm going to show you that LX is not going to be dominant. Okay. So you don't have to continue processing those 6 labels any further for the remaining objectives. The ones that pass through, they check. In this case, the second one gets dominated in the second label. And then finally, we find that even at objective 3, all of the labels are not dominant. So this LX is not dominated for all of these labels. Now I can exit. I don't have to check my objective 4, 5, and 6. So I save a lot of that unnecessary computation I would have had to do. So this early exit allows me faster processing, and we coalesce these labels on these vector lanes so that we can unlock parallelism at high locality, because what we do is we lay out labels per objective. In that way, when you bring objective data out, you bring a chunk of that data out from the GPU's memory, and it can be highly vectorized and processed in parallel. So that's our running operator and dominance operator. Now, in an efficient dynamic data structure, I'm going to just quickly run through this. The idea is that we process them in buckets. These nodes, we don't know how much memory I'm going to need for an open set or a closed set. It grows at runtime. So we have this idea of a bucket, and that bucket is going to allocate a new one and a new one as the arrays grow. Okay, so imagine that you have a bucket. Once you fill this bucket, you go to the next bucket. Once you first touch the next bucket, you allocate a new bucket. Okay, and in this example, now the algorithm runs in number 3, and it deletes and prunes labels. Right, so we create these holes. In parallel, you're deleting. We have an invalidation-based deletion mechanism where we don't have to reorganize the data structure and pay the price. So you, in place, delete them with flags. And then we have this whole compaction phase, where what we do is we traverse through our array, and we find the number of holes, and then we fetch from the end a valid entry and replace the hole with a valid entry. And that's how we compact this array before we offer it for the next iteration to compute. Okay, so this compaction phase allows me to keep these arrays compacted with valid labels. So my checks are not unnecessary. Otherwise, these holes I would have to check. There is a hole. Oh, okay, let's move on to the next. Right, and they allow me to manage my memory very efficiently, because now I can acquire and release buckets dynamically. This is really crucial in the GPUs, because GPUs don't have dynamic. So we enable this dynamic memory management with our protocol. The last thing is ordering. We have three things that we want to keep in open. There is the labels that I've extracted, the labels I did not extract, and the labels that I generated during my expansion. Right? These newly inserted labels have to be sorted. So we use a parallel sort on the GPU or a CPU parallel sort. And then all we have to do is just merge them with these non-extracted labels that are pre-sorted because they were sorted in the previous iteration. Right? And then we prepare the next open, and that's how the iterations flow. We have an optimization here that if the sum of these newly inserted and non-extracted labels is less than or equal to num extract, we don't have to sort. We're going to pop the whole thing in the next. So we have some optimizations here. So let me give you some quick ideas here on what we have found so far, and I'll wrap up. So we evaluated this on a GH200 superchip, which has a H100 GPU and 72 ARM cores. We evaluate this high performance C++ code for sequential. We have a parallel CPU and a GPU implementation. And we look at the number of labels processed for work efficiency measurements. We look at the parallel execution time with breakdowns for performance measurements. We use the road network graph. This is from literature. So in this road network graph, this is a New York road network graph. We create instances by picking source destination pairs. And these are then called so-called graphs. Each source destination pair generates a graph for processing. And then they operate with 4 objectives. In this case, these New York graphs come with distance, time, average degree, and the path length as 4 different objectives that we are co-optimizing. Some key results here. These are notorious. Road networks are notoriously hard to scale on in traditional graph analytics. They are no different in this setting because they have very high diameter, hops to goal node in our case, and they're very sparse. But still, we were able to reduce runtime by 3 orders of magnitude with our CPU parallel OpMOS, which we published in ICS this year. And we have a GPU parallel MPMOS, which is under review somewhere. We get 13x speed up for the CPU parallel, which is on those 72 ARM cores on that superchip, and 909x speed up with our GPU parallel.
What's the comparison then?
The sequential CPU, sequential implement in this particular. We have a US Navy's maritime routing graph. This comes from this template system. It's a future Navy capability. And it's an open source tool that generates these graphs. So we generate these graphs. These are state space reduced graphs. So they look small, but they are massive in terms of their computational complexity when it comes to objectives. The US Navy has released these 12 objectives. The first 4 are more distance, fuel, roll, pitch of the vessel. There is other aspects of the vessel that you're trying to optimize. And then there's all this weather parameters. And we use some ERA5 data set with wave heights. Then it gives us the time, the next 3-hour projections on the weathers. When we say X objectives or N objectives, we are taking the first N objectives from this list and co-optimize. If we can solve all 12, that's wonderful. We may not be able to solve all 12. For this, what we found was that we couldn't run all of them on the CPU parallel. So some of them only do 4 and 6 objectives because we just could not run them. In this case, we're getting 33x with our CPU parallel OpMOS and 3500x speed up on our MPMOS. This was the first time we have enabled maritime decision support for the US Navy in real time. They could not imagine doing this even with 2 objectives. They couldn't even run 2 objectives before we started already. There are a lot of interesting results here, but what we found, key point is, most time our MPMOS spends is on label processing. Only 10% we spend on compaction and only 6% we spend on sorting. We justify them because if I turn off my compaction, my dynamic data structures, we take a 2x hit. So that 10% is worth it. When we disable sorting and we don't order labels, we take a 5x hit. So and then our dominance checks with exits are 4x more efficient. So we validate all of these ideas. The last few slides, we looked at the scaling of these last two instances, there's last two graphs that we could not run to maximum objectives. The temp5 graph, we ran it to 12 objectives on our GPU and PMOS. It runs in 1 hour. On the GPU, at 12 objectives, our dynamic memory allocator consumes 25 gigabytes for labels. If I did not have my dynamic allocator and we statically use an oracle with multiple processing steps, find out the best configuration to run those dynamic structures, was 480 gigabyte. That is not available on that GPU. It's only at 96 gigabyte. This is H100 state-of-the-art GPU. This is 20x more efficient with our dynamic memory allocator. The last instance, we run out of the H100 96 gigabyte memory at 9 objectives. We can't run past 9 objectives. At 9 objectives, at 8 objectives, it solved it with 33 gigabytes. Okay, at 9 objectives, ran out of GPU memory. This is how big this problem is. This is the H100 GPU, this state of the art. You can't find a bigger GPU than that. So what we have demonstrated is that there's significant computational acceleration we can do in the CPU, in the GPU. There are key limiters. There's massive label processing. There's massive memory explosion because of the label, the way we process the labels. So there are some future directions. We're looking at some hardware-centric optimizations like asynchronous data accesses that we talked about earlier. There's this very tractable thing that we're doing where we want to take advantage of the CPU, GPU. We are a big problem. We are approaching LLM scale memory. So the GH200 was built for those LLMs because it enables access to the GPU, to the 480 gigabyte of the CPU memory through a NVLink, a terabyte per second NVLink. So we're trying to solve the temp2 problem now with the CPU. And then we want to keep looking at multi-GPU, disaggregated GPUs, hardware acceleration ideas. This problem is probably going to take the rest of my 10 years, probably at least, to keep solving. With that, I would like to thank a bunch of my old students and new students and upcoming students who have helped me with the graph processing work. A lot of my collaborators from UConn, from the US Navy, from different universities who I've worked with throughout these years. There's a lot of people here who I have talked to. So this is not an exhaustive list. These are some key collaborators. And special thanks to this guy, Leo, who's been working hard. He's my graduate student working on this problem. He's the one who is a fierce leader of this MPMOS project. He's just 2 years in and he is being extremely productive. So he deserves his own place in this talk. Thank you. Any questions? I'm sorry, I'm running. I need to compress this stuff. That's always a help.
I have one question. So,
Yes.
So since this is a multi-objective optimization, and I think there are a lot of performance speed up using the new proposed approach, right, compared to the single thread version you mentioned. But how do you compare the search result quantity, right? Because there's the single thread version generates one path that has this. I mean,
it generates multiple paths.
Right, with multiple paths, each path has different objective values.
But they are reproducible. So it gives you X solution paths. And those, we compute the exact same X solution paths with our parallel model. And we compare if they are exactly the same as a sequential. So we validate each time we run this instance, we validate all those paths. And you can trace back their path costs and they have to match.
But it's possible that that your parallel algorithm is going to find different paths compared to.
It is a deterministic algorithm. That's why we have that extra step in there where we don't let dominated labels be extracted in parallel and get into the solution set. We prune every single label that can be pruned out. We give you a Pareto optimal frontier at the end.
So
in the
it
solution.
exhausts all the paths.
Yes, it gives you the exact solution, exact Pareto. It's a very good question. That is why we're doing this.
Okay.
The only reason why we're doing this is because we want to give you exact solution paths. There are algorithms of multi-objective optimization that approximate those facts. That is how a lot of the people in the literature have tried to make this practical by approximating them. We have been computing these with exact solutions. That's why this is so hard. Now, there is another avenue of future work to trade off accuracy with performance, where you can give up on accuracy. There has been no work where the inaccurate or approximate solutions, where people can quantify and say that these solutions that I produce are quality solutions. You didn't have something to look for. This enables, our work enables exact solutions. So now you have an exact set of solutions. And now you can say, okay, I can compute an approximate solution. And now you can measure against that and say, okay, how good are my approximate solutions? So there is an average algorithms that can now correlate with our work, where we can actually give you exact solution. There is a lot of potential in that. The operators, because they actually, when we were given this problem, back they're like, they're my friends here, right? Right. So they approximate solution.
But
And
then
they
if
they couldn't.
if the graph becomes much bigger, then it's
Yes.
possible to take too long to get.
Yes, so they do it. So what you do is traditional graph algorithms on the graph the road network, right? You want to go from Manhattan to say Long Island. You don't need to traverse and upstate New York, right? So you can prune that graph out very quickly, and so you can create a much smaller instance that you now need to perform this optimization. And that's the same thing that we're doing on our land sea graph. The vessel is routing with physics, is moving with the speed. Space, right? So we aggressively state space reduce that graph and then generate that instance. That is where you try to then solve this problem. If you go to large graph with anything bigger than this problem explodes very quick. I mean, even here you're seeing, right? I mean, the explosion here is ridiculous. Yeah. Anyway, good question. Any questions from you guys back? Thank you for coming. I know it's a holiday time, and I was here. I thought that I'll come talk to these guys, and why not present you to the logic.
Well, thanks for visiting.
No, it was great. It's great. Every time I come to Orlando, it looks newer.
Yeah.
I don't know what's happening. I mean, cities get older, then city keep getting newer.
It's dream here. When you're only looking at stuff, you look at people,
They are getting older. That's right. That is probably true. Okay. Yeah, that's a good point. Yeah. Yeah. I was trying to be optimistic. All right.
Yeah.
Okay. No questions? Anything online? Okay. All right. Thank you guys online, everybody.
Okay, thank you, Omar. Sorry, I have
Please.
some internet issues, so I'm not able to, follow exactly. So I'm gonna
Okay.
stop the recording on my side. So hopefully the recording is all good. And one last question for you is that do I get the permission to make it public on YouTube?
Sure.
Okay, sounds great. Thank you so much for the great talk.
Yes. Thank you.
Yeah,
Bye-bye.
catch up with you later.
Yes.
Oh.
I'll catch up with you later. Thank you so much.
Bye.
Bye.
Yeah. But you